say we have f of x is 1 over x. Now, first we want to find the area. Okay. Area in 1 through infinity under this curve. Okay. I'm going to throw that thing in. So that thingy looks about like this, right? And then we cut it right here. This is 1 and that infinite area. You know what I'm saying? Okay. Actually, I don't want those. Okay, that of course we integrate. So we have 1 to infinity of 1 over x dx. Good. And first thing we do is, this is our review. We write it with proper integral, b approaching infinity and 1 to b 1 over x dx. And that is ln. And we are sure, right? ln x from 1 to b. Notice that I didn't bother to write absolute value again. I mean, you could write it. I'm not that picky. It's just redundant. Okay. And substitute limit of b approaching infinity of ln b minus ln 1. And ln 1 is 0. So what we have here is ln b approaches infinity, correct? This approaches infinity and this is 0. So what we have is infinity, and we knew this is infinite area. Right? Okay. Now the question is, what is the volume of this if you rotate it about the x-axis? What? Would that obviously be infinity as well? Because if you rotate the infinite area, I'm going to recycle this picture. Okay, if you rotate this infinite area, so we have f of x still is equal to 1 over x. And what is the volume? What do you say? Would that be infinity? Let's review disk method. So I'm going to draw the rectangle. Let's say, whoa, hold on. Why is this rectangle ugly? I'm going to put it. Okay, let's just resize the darn thing. Really? Yeah, like that. Okay, so if I rotate that thing around, then I'm going to create the disk, which looks like this. That's my dv, right? So let's get the dimensions. This is dx and that height is y. So my dv then is pi r squared y squared times dx, isn't it? And of course my y is 1 over x, so that gives me pi 1 over x squared dx. Still with me? Okay, let's evaluate that. So my volume is integral from 1 to infinity and pi and then 1 over x squared dx. Writing as proper integral. So b approaching infinity of, I'm going to take pi out, and I'll just leave the pi inside. So 1 to b, and then we have pi, and then x negative 2 power a. You with me so far? So we'll have limit b approaching infinity of, now I'm going to take pi out here. Good. And then we'll just have x to the negative 1, so negative sign 1 to b. And using plumbing professor as always, so we have pi, limit b approaching infinity, and then this one first, 1 minus 1 over b, and 1 to b. Now, if we take the limit, this one dies. Good. So we get pi.
You don't need the like brackets and B1 for the last step.
Oh my god. There. Okay. Now, what just happened here? How can we rotate the infinite area and get a very small finite number? I still haven't got the answer to explain this phenomenon. Then one begs the question, what about the surface area? And this is a real review of this chapter, so that's what I really wanted to do. This is what your book calls it, the Gabriel's horn, I think. This thing is famous, so it has a name because you rotate the infinite area and you get the finite number. Like, how is it even? You see how infinity, how screwy they are? Okay, so finally, then we still have the same function, but now we want surface area. Of rotating that thing from 1 to infinity. Oh, care to guess? It's kind of anybody's guess at this point, right? Is it infinity or is it finite? What do you guys say?
Infinity.
Infinity is a vote. Does anybody want to vote for something else? That's my DS. And I'm going to rotate this thingy. Infinity is the only vote.
I don't think it's infinity.
Okay, so I have one infinity and one finite. So do we have a tiebreaker? I messed up. Kind of like that, right? Okay, so that's my ds, but in order to do ds, we need, well, dA, but we need ds. In order to do es, we need dy over dx, right? So let's do that first. Dy over dx, -1 power, so is it -1 over x squared? Then we can do ds. ds is square root of 1 plus that thing is squared. You with me? And then, of course, dA is, let's get the dimensions. This is y right here, right?
Wait, shouldn't it be 1 over x to the 4th?
Oh my god, I'm making so many mistakes today, eh? Nice catch. X to the 4th. Lively class. Whoever's watching this video, this is an actual class. I have students on the other end of this. I'm not just talking to the computer. This is real high school. Okay. Now, so we have circumference 2 pi y times ds. You still remember the surface area thing? Okay, so that becomes 2 pi and my y is 1 over x, correct? And then ds. 1 plus 1 over x to the 4th power dx. How are we going to integrate that thing? Are you worried yet? I'm going to find the common denominator of this. So I'm going to put x to the 4th plus 1, and you will see why this is clever, and all that work I want to do it before I put it inside the integral. Okay? So far with me? Okay, then, so this is in reality 2 pi and then square root of x to the fourth plus 1 over, this becomes x squared, so x cubed. Say yes. Okay. I'm going to integrate now. So my surface area, what do you want to call it? ASS is equal to 2 pi integral from 1 to infinity of that thingy. Now you're getting worried, right? We don't know how to integrate this. Maybe we do, but we don't want to try. I think there's a way, change a variable, but no, I don't want to try. All we want to answer is it convergent or divergent? So what should we compare this thingy to? Now would be a really good time to give a brilliant suggestion here. What do we compare this integral to? I'm going to still put 2 pi here.
Square root of x to the fourth power over x cubed.
Yes. You know, whatever, like, only thing that messes us up is that thingy, right? So we just remove it and it's very, very nice. Now we have enough confidence that we can integrate this. You know what I'm saying? Okay, you notice that I didn't put the direction of inequality yet. I want to know if this thing is integratable first or not. So, well, this is nice. So we'll put 2 pi and then we'll write it with a proper integral. And from 1 to b, and that thingy is just 1 over x now, isn't it? And we have seen this movie before. You know how this story goes. This is 2 pi, limit b approaching infinity, and that's ln, and we are sure? You with me? Okay. And then this is 2 pi and limit b approaching infinity of ln b minus ln 1. And when we take limit, this approaches infinity and this is equal to 0, right? So what we get out of this is infinity. This is divergent. If this side is infinity, God, I wish the inequality direction is that way, right? Do we have this? Is this inequality true? Yeah, it is, because see, that's 1 here, so numerator is slightly greater here. So this is greater than or equal to this thing. That tells you this whole thing is divergent. So we have infinite area. Now, you see the process, how I decide which test to use. I am not deciding until I work this thing out. Then I will see which direction do I want. Do I get the direction that I want? You know what I'm saying? Now, if this direction does not work out, then guess what I'm going to do? Then I'll proceed with limit comparison test. You get it? Then that'll work out nicely. Now, at this point, how many of you want to see limit comparison test? Nay? Yes? No? Okay, enough people. So I will do a limit comparison test. This is optional, okay? Because we got the direction correctly. So direct comparison test will do, but optional limit comparison test. Oh, my handwriting is messy. Okay, I'll do that. And the way you do that is you take a limit of x approaching infinity of this thingy that we want to study over x cubed over thingy that we are comparing it to. We want to evaluate this limit. Okay, let's see what that thingy becomes. And then you see x cubed cancel. So easiest way to do this is like this. That one looks ugly. You know what I'm saying? Do you see that's obviously equal to 1? Or you can L'Hopitalise things inside, then one derivative later, you see that is 1, right? So this thing works out too, but since we got this direction correctly here, we don't have to do that. This one is easy enough to see. So direct comparison test is preferable in this case. Good. So this one diverges, right? That infinite area. And one can say, yeah, that's more area than that little strip of area because we rotated that thing around. Okay, fine, we can see that. But what I still don't understand is how come this is convergent? Is it because maybe this area, this one and the first one is two-dimensional stuff, and this is three-dimensional stuff? I mean, that's the only difference I can see. But I still don't know why that one alone is convergent. Any ideas? Shifan?
I did so I put the function for the volume over function for area and took the limit to infinity, and it showed 0. So it means that the function of area grow much faster than volume when it goes to infinity.
Oh, so it has to do with the growth rate, huh? Okay. Okay. Maybe, huh? I mean, that's the best explanation we have at the moment. Okay. Do you guys know what this thing looks like? Do you see it peaks at the top and then dies down on both ends? Okay, why don't we feel it together, right? Okay, that's the first thing, that you have to know kind of what it looks like. So, say we have this thingy. If you substitute 0, right, what do you get? You get 1 and 1, so we have 1/2, right? Say 1/2 is up here. And do you see this thing dying out like this? Let's see, if you approach infinity, this thing becomes infinity and this thing becomes 0. So it's still 1 over infinity, right? If you approach negative infinity, this thing becomes 0, but this thing becomes infinity. And then one more thing we should check is this an even function? Sure it is, right? This is an even function. Because if you substitute negative x instead of x, then this whole thing is exactly the same as before, right? So this is an even, whoa, what did I do? So it is an even function. So wow, then we don't have to, well, we are still breaking it up, but we don't have to do 2 separate integrals, right? We can do 1 integral. So that's nice. That's number 1 thing. So this thingy is equal to, now we'll say 2. And from 0 to infinity. And then the other trick I'm going to do is I'm going to multiply e to the x here, here, here. And let's see what happens, okay? So we have e to the x dx over, wait a minute, I'm going to put this work glove on so that it doesn't interfere with touch screen as much. And then this becomes e to the 2x, and this becomes 1. You know what I'm saying? Very good. So we have only 1 improper integral at the top end. Good. Okay, now, do you recognize this thing? I think I have done it once before, maybe twice. We do a trig sub. This is x squared plus 1 format. So we let e to the x to be tangent theta. Once you do that, then you derivative on both sides. So we have e to the x dx becomes secant squared theta d theta. And this denominator, which is our biggest motivation with the trig stuff, this thingy becomes tangent squared plus 1, which is their secant squared. Then magic happens. So we have 2. Now, this over this, which is just the theta. That is nice, right? Now, let's change the limits of integration. Substitute 0 here. You have to be careful. If you substitute 0 here, this thing does not become 0. This thing becomes 1. You know what I'm saying? So tangent theta is equal to 1. What's theta? Inverse tangent of 1, which is pi over 4. That's a common mistake. And then once this thing approaches infinity, right? Where's the vertical asymptote of tangent that gives you infinity? Okay, there. Wow, we didn't have to take a limit and convert it into proper integral. That's one benefit of trig stuff. The functions that has vertical asymptote tends to give you this. Well, some people might say that's technically trig stuff because there's a vertical asymptote, right? Well, that's in a way, right? This is still improper if there is a tangent in it, but we don't have tangent in it, so we're good. So this is 2 theta and pi over 4 to pi over 2. And that's just pi over 4 minus pi over 2, which is pi over 4 times 2. So we have pi over 2. Bang. Huh. That is very nice, isn't it? Yeah. Now this thingy, what we want to do is this. What do we want to compare this thingy to? 1 to infinity of ln z over z dz. And of course, we want to compare this thingy with 1 to infinity of 1 over z. That makes sense to you? Right, then ln z is greater than 1 as it approaches infinity. So yeah, and then we know this thing eventually becomes divergent, right? We have done this thing before. This is infinity. Eventually this will be infinity. Oh yes, great. So inequality is that way, end of the story, right? All we have to do is just evaluate this improper integral. There is a one little flaw. What is the flaw? The flaw is this inequality is not always true. Whenever you write an inequality, you have to, or any statement in math, you have to ask yourself, is this statement always true? And the answer is no, it's not. See, ln z is not always greater than 1. What? Let's just think about it. I want to know where ln z, we have this inequality, ln z greater than 1, right? I want to know where that is true. Okay, number one, if this z is less than 1, this thing is negative, so it's definitely not true, right? But even if it's more than 1, is it still true? Let's take e on both sides, right? So this thing z, and this thing becomes e. You know what I'm saying? Oh, z has to be greater than e for this statement to be true. Let me show you graphically, okay? I'm gonna copy that thingy and make it appear magically on the side. Okay, let's see this graph. Make that a little bigger. See, this part is ln z over z, and this thing is 1 over z, right? At this between nf, beyond this is negative because ln less than 1 is negative. See, it's clearly underneath that, so we cannot say this inequality is true. And it starts becoming greater than 1 over z at E, as you can see here, right? So there's a little thing that we have to do. Well, then all we have to do is just change that to E. What are you doing? This is what I'm doing. This integral is from 1 to E of ln z over z dz, that z is ugly, plus, and then e to infinity of ln z over z dz, correct? Now, this is a finite number because there's no vertical asymptote 1 to e. That's like that area right there. You get it? So that's a finite number. Only convergence or divergence depends on this part, this tail end. Is that infinity or is that finite number? And I'm trying to show, well, with this is of course infinity. So if that's the infinity, then whole thing becomes infinity is what I'm trying to argue here, right? So, but before I can compare these two with a direct comparison test, I have to make sure this is always greater than that thingy everywhere that I'm integrating. So I have to start this lower bound from E instead of 1. You get it? Any questions about this part? Okay, I'm going to put that inequality in the corner. Now I will start evaluating and finish this work. Okay? So this thingy now is equal to, now we still have to rewrite it into proper integral b approaching infinity of e to b and then 1 over z dz. And this is ln, and we are sure that negative 10-point rule still applies if you write down ln when you're not supposed to. Somebody on the previous test came very close. Good. Say yes. And limit as b approaching infinity of ln b minus ln e. And what is ln e? ln e is? Somebody tell me what ln e is.
1.
This is 1. And of course, this approaches infinity. You get it? So we have infinity. So now, of course, our integral is divergent then, right? So we can say our integral is divergent. How about that? Good. Now, say you want to avoid this case, because this is like somebody from the second period was asking, like, how do you think like that in the middle of the test, right? Say you don't want to avoid, you don't want to think like that and don't want to figure this out. Then what is a nice way of doing this same thing? You do a limit comparison test. You get it? So let me show you a nice little alternative. Here's an alternative limit comparison tests. That's an ugly and limit comparison test. Okay. So all we have to do is this. You are comparing these two, right? Actually, that's a bad one to compare it to. No. Actually, no, I cannot really do limit comparison test in this case. Because if I compare this with this, I don't get finite number, right? That's a headache, isn't it? We can still argue like this. We can still argue like this with the limit of ln z over z and 1 over z, right? Z approaching infinity. And that is, of course, z approaching infinity of just ln z, and which is infinity, right? Now, then we figured out limit of this thingy is infinity, right? So, and limit of 1 through infinity of 1 over z dz is equal to infinity. Now, that tells you ln z over z is growing a lot faster than 1 over z, this thingy. You know what I'm saying? And this is already infinity, so do you see that this has to be even bigger infinity? You know what I'm saying? So we could make this argument, therefore this. This is divergent. But this, I don't like this argument a whole lot. Because we like to get the finite number from the limit comparison test, but this still works, right? It's a bigger infinity. I will accept both on the test in case you see something like this.